Okay, so we're coming back with these encryption methods, and this is just a picture of what a block cipher looks like. This encrypts data in blocks, right? Which is most of the symmetric ciphers do that. And then there is also the stream cipher, right? Which you take a key, and we said this encrypts data bit by bit, right? There's only one symmetric cipher that does that. The rest are all asymmetric. Okay, there's a good picture of that there. I hope you enjoy. So with the symmetric algorithms, right, as the ciphers get stronger, others worked, I mentioned in the opening slide, to break them. So standards continue to get more stringent. And this is just an example of that process. Yeah, you can find more of it in the reading to describe it. Eventually then we end up with, so we have this DES, this new standard DES, which we'd already talked about a few slides back. Well, DES was broken, so they came out with triple DES or 3 DES, right? And this served as a quick fix to the DES encryption issues. And then 3 DES performs the original computation, but it does it 3 times, right? And the price, of course, as you already know, is in performance. So it takes longer to encrypt and decrypt a message. So continuing along that line, eventually NIST decided on a new standard. A new standard would be an order for advanced encryption. And so they called it the Advanced Encryption Standard, or AES, the Advanced Encryption Standard. And what that did was in symmetric block ciphers, now we're capable of encrypting in support of 128, 192, or even 256-bit keys. And so in this way, the International Data Encryption Algorithm, known as IDEA, comes about. And this is a block cipher that operates on the 64-bit block of plaintext. And it uses a 128-bit key and is used in PGP, called Pretty Good Performance. It's a free for non-commercial use. We'll talk about PGP in a little bit. So after that, then we get Blowfish. Blowfish then is another block cipher that operates on the 64-bit blocks of plaintext. However, the length of it is variable. After that was developed RC4. This is the most widely used and I think only stream cipher. RC4 is the only stream cipher of the symmetric algorithms. The rest are all block ciphers. And it's used in web wireless encryption. So RC4 is considered difficult to break, but frankly should be avoided for most applications. And then we have RC5 symmetric algorithm. And it's a block cipher, right, that can operate on different sizes, block sizes like 32, 64, or even 128-bit. Now what I did was I put here from some great slides that I've made before, the algorithm tables. And at the top, they are symmetric algorithm tables. And on the bottom, I list some asymmetric algorithms, just to give you kind of the distinction, the detail and the distinction between those. You'll see RC4 is the only stream cipher of the symmetric. Okay, asymmetric is stream cipher. Okay, so then we move to asymmetric algorithms. So it's here, instead of a single key used like in symmetric algorithms, asymmetric algorithms use 2 mathematically related key, right? Sometimes we'll also call this the public and the private key. So the data encrypted with one key can be decrypted only with the other key. Another name for the asymmetric algorithm is the public key, as I mentioned, or even sometimes called public key cryptography, right? Those terms are kind of used interchangeably, that and asymmetric algorithm, etc. So a public key is openly available. It'll be on some server or published. Access is available. A private key, however, is the secret key. It's only by the key owner and should never ever be shared, right? So the private key might be on my computer, and when I encrypt a message with my private key, I send it out, and somebody else with the public key can decrypt the message. So even if people know the public key used to encrypt the message, they can't figure out the key owner's private key. It's a secret. So in addition, this asymmetric capability, it's scalable now, right? Because only one public key can be used by thousands of users, right? As opposed to symmetric, where I have to create these new keys all the time. Okay, so so here's how it works, right? So user A is going to encrypt a message with a private key. That's me. I'm sitting at my computer, and I'm going to send it to you, right? Your user B. And user B, then you're going to decrypt the message using my public key, right? So if confidentiality is a major concern for me, right, what I'm going to do is encrypt the message with user B's public key and send it to you, your user B, right? I'm going to send it to you. And you will decrypt that message with your private key, right? Which only you know. Now, I mentioned some asymmetric algorithms, and RSA is certainly one of them. It's the first algorithm used for both encryption and digital signing, and it's still frankly widely used, right? Many web browsers using the transport layer security, or TLS, right, protocol, they use RSA algorithms. A simple analogy might be making a smoothie, right? So it's easy to blend the banana and the strawberry and the ice cubes in a blender, right? I can do that at home. But if you have to reconstruct the banana itself, or the strawberries, or the ice cubes into the original state after you've blended them up, that becomes an impossible task. And that's really what asymmetric algorithms are all about. RSA being the first, as I mentioned, that would do both encryption and digital signing. It's important to mention Diffie-Hellman. Diffie-Hellman really doesn't provide encryption, but it's there to establish one secret key shared between two parties. It's really a key exchange vehicle. Think of it that way. Now, other asymmetric algorithms include ECC, or elliptical curve cryptography. This is a very efficient algorithm requiring few resources, right, like memory, disk space, or bandwidth. So it's a really good candidate for wireless devices and cell phones for encryption. Now, there's Elgamal, right, which it's used to generate keys, encrypt data, and create digital signatures. And it was written, it's named after the inventor. And you can read more about that in the book. Then we touch on the topic of digital signatures, right? So using this public-private key pair, a public key, remember, can only decrypt a message that was encrypted with the corresponding private key, right? And so digital signatures create this effect. The hash created from the message content is encrypted and then with a private key to ensure that authentication and non-repudiation. Those are the two key words with digital signatures: authentication and non-repudiation. So this is a picture of how that process works. So we start with somebody typing an unencrypted message. They will generate a hash value. They will encrypt it, and the receiver can view this with the sender's public key and compare the hashes to ensure authentication and non-repudiation, which is really the goal. Now, digital signatures were established by NIST, the National Institute for Science and Standards and Technology, in 1991, right? And the federal government, NIST is actually a U.S. government standard, right? So it makes sense, the federal government then requires RSA and digital signature algorithms be used, including the NIST required SHA, or secure hash algorithm. Now, continuing in this line of thought with asymmetric encryption and digital signatures, so pretty good privacy can be utilized. So the federal government, as I mentioned, specifies using RSA and digital signature algorithms, or DSA sometimes it's called, right? And so for all digital signatures, this is to be done. And using a hashing algorithm, it ensures the message's integrity. Remember, CIA, integrity. And that's where we get this non-repudiation from, that we can prove integrity. So NIST requires using the SHA, or secure hash algorithm. So PGP is nice because it's a free encryption program, can be used for email and other things, right? The internet standard for PGP is now actually called OpenPGP. And OpenPGP uses certificates, right? PKI certificates. It's similar to PKI certificates, but the certification authority isn't used, and it's not as efficient, right? That's about all you have to know for this course. And the most common free version of OpenPGP today is called GNU Privacy Guard. GNU Privacy Guard, or GNU PG, or sometimes it's called GPG, right, for GNU Privacy Guard. But that is the most common free version of OpenPGP, or pretty good privacy. Pretty good privacy. I think I said pretty good performance earlier. It's pretty good privacy. Now, digital signatures continued. And so this GPG that we just talked about, it's useful for understanding how public key encryption algorithms is used. And like I said, best of all, it's free. OpenPGP is not the only technology, though, for sending secure emails, right? And these others listed here are incorporated: AES, IDEA, RSA, DSA, and SHA, of which we've discussed several in this conversation already. Now, continuing with digital signatures, we have a secure multi-purpose internet mail extension, right? Or SMIME, as sometimes it's called, right? S/MIME. This is another public key encryption standard for encrypting and digitally signing your emails. Microsoft it's built into Microsoft. So it can also encrypt emails containing attachments, which is great, and uses PKI certificates for authentication. As I mentioned, it is built into Microsoft. And so as a security tester, sending test results from a company and that reveal vulnerabilities, which are subject to interception, this can be a very serious vulnerability for us. So we want to make sure that we've encrypted our email messages using SMIME. We don't want to contribute to our clients' network security problems, right? So we want to make it a policy to exchange test results or other sensitive documents in this sort of encrypted form, right? it can be a challenge, right, for many. Okay, we'll come back with the third part of 3 next.